Hello and welcome back to the channel. Today, we are diving into a series of high-discrimination VCE Physics Newtonian mechanics questions, specifically covering questions 7 through 13. Now, before we jump into the paper, look at this stat from the official examiner's report. 67% of students across the state scored exactly 0 marks on this vertical spring question. Why? Because they fell into a massive conceptual trap that looks incredibly simple, but completely ruins your entire paper. In this video, we are unpacking the exact mechanics behind these questions. I'm going to show you the one golden rule that will instantly save you from this 67% spring trap, and how a sneaky keyword in collision questions tells you exactly how to secure full marks without guessing. Let's get into it and unlock these marks. A model car of mass 2.0 kilograms is propelled from rest by a rocket motor that applies a constant horizontal force of 4.0 N, as shown below. Assume that friction is negligible. Which one of the following best gives the magnitude of the acceleration of the model car? To calculate the model car's acceleration, we use Newton's second law, which states that acceleration is directly proportional to the net external force and inversely proportional to its mass. Which one of the following best gives the magnitude of the impulse given to the car by the rocket motor in the first 5.0 s? Impulse is defined as the product of the net force and the time interval over which it acts. Substituting the values for force and time into this relationship yields the magnitude of the impulse. With the same rocket motor, the car accelerates from rest for 10 s. Which one of the following best gives the final speed? Using the mass and net external force given in the stem, the final speed can be found in two ways. Method 1, kinematics first, find the acceleration using Newton's second law, from question 7, then use the linear motion formula to calculate the final speed. Method 2, impulse momentum, apply the impulse momentum theorem. By relating the net force and time interval directly to the change in momentum, you can solve for the final speed in a single step without relying on previous answers. Both approaches produce identical results. Risk isolation, mitigating error carried forward. Method 1 forces students to use their calculated answer from question 7, acceleration. If they made a silly calculation error earlier, that error automatically cascades into question 9. Method 2 relies only on the raw data provided in the original prompt, F and M, completely isolating question 9 from previous mistakes. Elegant logic chain. It provides a cleaner, single-step conceptual framework. Instead of breaking the motion down into force, acceleration, speed, it treats the interaction as a whole, looking at the cumulative effect of force over time. Reinforcing key concepts. Because question 8 just introduced the concept of impulse, method 2 naturally reinforces that knowledge, allowing students to see the direct physical application of impulse turning into kinetic momentum. A model car is on a track and moving to the right. It collides with and compresses a spring that is considered ideal, as shown in the diagram below. The car compresses the spring to 0.50 m when the car comes to rest. The force-distance graph for the spring is also shown below. Assume that friction is negligible. Since the spring is ideal and friction is negligible, Hooke's law applies. Therefore, the spring constant is simply the slope of the force-distance line. To find this, we select 2 points on the line, substitute their values into the slope equation, and calculate the result. With no frictional losses, mechanical energy is conserved, meaning the initial kinetic energy equals the final spring potential energy. Approach A, area under the graph. Find the area of the triangle up to delta x equals 0.50 m. This independent method uses only the provided graph values. Approach B, algebraic formula use E equals 0.5 times k times square data x, with the value of k calculated in question 12. Exam tip: approach A is preferred on exams. If you made an error calculating the spring constant in the previous question, approach B will cause a consequential error, whereas the area method isolates your risk. Now, we are unpacking a classic 3-mark VCE conservation question from question 12. Before jumping into the math, let's carefully deconstruct the question stem. We are presented with a 2-body system where a faster, heavier trolley A, catches up to a slower, lighter one, trolley B. The phrase "locked together" in the text is your ultimate physical cue. It explicitly dictates a completely inelastic collision model, meaning the 2 separate masses will combine into a single, unified mass, 6.0 kilograms, post-collision. To determine whether the collision is mathematically elastic or inelastic, we must verify if the system's total kinetic energy is conserved. Let's break down the perfect response step by step to secure all 3 marks. Many students lose marks here not because their math is weak, but because they misinterpret the diagram or skip a crucial logical step. Let's break down the perfect response step by step to secure all 3 marks. Step-by-step solution. Step 1. Calculate initial kinetic energy. Before the collision, both trolleys are moving independently to the right. Step 2. Find the final combined velocity. Because the 2 trolleys lock together, after the impact, momentum is conserved, allowing us to find their shared final velocity. Step 3. Calculate final kinetic energy. Now, calculate the kinetic energy of the combined system moving at this new velocity. Step 4. Justify and conclude. Compare the total energy before and after the event. Since the total initial kinetic energy is not equal to the total final kinetic energy is not conserved, 6.0 J is lost, therefore, the collision is inelastic. Police cars revolving light chief assessors alert. Common student errors. To make sure you don't drop easy marks, be highly aware of these 2 common pitfalls highlighted in the official examiner reports. The halfway halt. The most common error was calculating the initial kinetic energy of the system, 54 J, but failing to calculate the final velocity, and therefore the final kinetic energy. You cannot prove a collision is inelastic without mathematically comparing both sides. The frozen diagram trap. A number of students incorrectly interpreted Figure 10b as stating that the final velocity of the system was 0. Remember, locking together simply means they join as a single mass, it does not mean they come to rest. They are still sliding to the right. This question is a high-scoring 3-mark question that separates the top-tier physics students from the rest. The question asks us to find how far a spring stretches, x, when a hanging mass is released from an unstretched position and comes momentarily to rest at the bottom. At first glance, this looks like a straightforward mechanics problem. However, looking at the official examiner's report, a staggering 67% of students received 0 marks here. Let's merge the ultimate exam trap with our secret weapon tool to see why so many fell through the floor, and how you can lock in full marks. Police cars revolving light, the milligram equals kx trap, and the golden rule. The examiner's report noted that the most common error by far was to blindly use milligram equals kx. Why students fail? Students see the phrase, comes to rest, and their intuition instantly screams forces are balanced, so downward gravity equals upward spring force, milligram equals kx. If you do this, you get x equals 0.98 m, which is exactly half of the correct answer. The reality, the overshoot, the equation milligram equals kx only defines the equilibrium position. When the falling mass reaches this point, it doesn't stop, it is actually moving at its maximum velocity. Due to its massive kinetic energy, it violently overshoots equilibrium and keeps stretching the spring until all energy is completely drained. At the very bottom, it isn't balanced, it is undergoing a violent, emergency brake, where the upward spring force is actually double the gravity force, which is why it instantly bounces back up. Electric light bulb, your golden rule for vertical springs. Always check the release method in the question stem. If it says slowly lowered, the mass never builds up speed and rests at equilibrium. Use forces, milligram equals kx. If it says released or dropped, the system is dynamic and overshoots equilibrium. Use energy, mgx equals 0.5 times k times square x. Step-by-step solution. Since this mass was released and allowed to fall, we must apply conservation of energy from the top to the very bottom. Loss in gravitational potential energy equals gain in elastic potential energy. Step 1. Set up the energy equation. Step 2. Substitute and solve for displacement, x. Using the precise values given in the question stem, and VCE standard G. Since the maximum extension x is not 0, we can safely divide both sides by x. Correct answer. The spring stretches 1.96 m before coming momentarily to rest. Explain how the three energies involved and the total energy of the mass vary as the mass falls from top to bottom. Calculations are not required. 4 marks. This question a 4-mark explanation question that requires absolutely zero calculations, but demands flawless conceptual precision. The official examiner's report reveals that this question was a complete minefield. Most students lost marks here not because they didn't know what a spring was, but because they fell victim to lazy intuition and superficial descriptions. Before we look at the correct answer, let's look at the 4 fatal traps highlighted by the chief assessors, and the conceptual hooks you need to bypass them. Trap 1. System energy versus mass energy, the conservation blind spot. The error. A massive number of students wrote that the total energy of the mass remains constant due to the conservation of mechanical energy. The hook. You must distinguish between the system and the individual component. Because friction is negligible, the total energy of the entire system, mass plus spring plus earth, is conserved and stays constant. However, as the mass falls, it is continuously doing work on the spring, transferring its mechanical energy into elastic energy. Therefore, the total energy of the mass alone, e.g. plus ek, continuously decreases during the descent. Trap 2. Stating states instead of trends. The error. Many students only described fixed snapshots, writing things like kinetic energy is 0 at the top and 0 at the bottom, while spring energy is maximum at the bottom. This scored 0 because the question explicitly asks how the energies vary, change. The hook. Avoid static descriptions. You must explicitly state the dynamic, continuous trends using action words like continuously decreases, continuously increases, or increases then decreases. Trap 3. The energy relay race myth. The error: students frequently wrote that the energy starts as all gravitational at the top, converts entirely into kinetic in the middle, and then converts entirely into spring energy at the bottom. The hook: real-world physics is not a relay race where one energy completely hands off a baton to the next. Aside from the exact release point, all three forms of energy coexist simultaneously and change smoothly at the exact same time. Trap 4. The kinetic dominance illusion at the midpoint. The error: many students asserted that at the midpoint, equilibrium, most of the energy has been converted into kinetic energy. The hook: trust the math, not your eyes. At the equilibrium midpoint, the kinetic energy does reach its peak, but it only accounts for 25% of the system's total energy. The spring holds another 25%, while 50% of the total energy is still held as gravitational potential energy. Therefore, gravity, not kinetic energy, is still dominant at the midpoint. Full mark response breakdown. To secure all 4 marks, your written response should trace each energy trend continuously from top to bottom. Gravitational potential energy, e.g., because the mass is continuously losing height as it falls, its e.g. is maximal at the top and continuously decreases throughout the entire descent to a minimum at the bottom. Elastic potential energy, S, because the spring is continuously stretching further from its natural length. Its S is 0 at the top and continuously increases throughout the entire descent to a maximum at the bottom. Kinetic energy, EC, the mass starts from rest, EC equals 0, and accelerates downward while gravity exceeds the spring force. After passing the equilibrium midpoint, the upward spring force exceeds gravity, causing the mass to decelerate until it stops at the bottom, EC equals 0. Therefore, EC increases from 0 to a maximum at the midpoint, and then decreases back to 0 at the bottom. Total energy of the mass, e.g. plus EC, because mechanical energy is being continuously transferred out of the mass and stored in the expanding spring, the total energy of the mass itself continuously decreases from top to bottom. (1) Collisions and graph strategy. Inelastic Q, locked together, always implies a completely inelastic collision. Prove it by checking if initial total EC is equal to final total EC. Risk isolation. On multi-part graph questions, choose the area method over formulas using a previously calculated K. It utilizes primary data, eliminating compounding or consequential errors. 2. Vertical spring dynamics, the 67% trap. The overshoot. A dropped mass does not stop at equilibrium, milligram equals kx. Due to momentum, it overshoots and comes to rest momentarily at maximum extension. The golden rule: slowly lowered static equilibrium. Released or dropped dynamic overshoot. 3. Continuous energy trends and the midpoint split. Mass versus system. The total energy of the system stays constant, but the total energy of the mass alone, e.g. plus EC, continuously decreases as it transfers energy to the spring. The energy relay myth, e.g. EC and S do not take turns, they coexist and vary simultaneously throughout the descent. The midpoint split. At the equilibrium midpoint, EC peaks but does not dominate. If you need my help, you can add me on WeChat or WhatsApp, or send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.